So thank you very much. Okay, so well, I am Francisco Ansedes from AIMEN Technology Art Center, and I'm going to talk today about the ATL FFF multistage manufacturing that we are doing in the Domino project. Okay, so first of all, we will go more into detail of this later, but just to have a glimpse of the technologies that we are using here, we are using AFP and FFF technologies that are two different technologies for composite manufacturing. AFP consists on depositing composite carbon fiber on tape format, and in FFF we deposit filament format composites. So for this project, we have chosen, and we're working with thermoplastic because of various properties that they have, their reprocessability, reparability, disassembly properties, recyclability, weldability, and as well as the possibilities of in situ consolidation that we will talk about later. And we have chosen the high performance thermoplastics because of their mechanical properties, good mechanical properties. So in particular for the AFP, we have chosen Allen Pike UD tapes that you can see here, UD tapes for AFP manufacturing. And for FFF, we have chosen PEC matrix for building the composite materials. So in this case, for FFF, we have three kinds of materials. We have in first place the continuous carbon fiber filaments that will have a structural function. We have also the carbon nanotube fiber reinforced filaments that Carlos talked before in his presentation that will do the structural health monitoring function. And we also have magnetic nanoparticles reinforced filaments that will have properties that will allow the disassembly of the structures. So going into the multi-stage process, in this case we are using a multi-stage robotic-based production because both the AFP and FFF are robotized technologies that are mounted on robotic arms, and in the Domino process we alternate between the two stages. We laminate and we lay up the UD material, the UD tapes with Allen Pike matrix to be the structural monolithic skin of the parts, the panels, and we will lay up with AFP. Then we add the carbon nanotube reinforced filament. And well, you can see here also is you can see the carbon nanotube and the PAKK PEC matrix. We have this format. We manufacture this format in order to print it with the FFF on top of the laminates and to cover it again. So this carbon nanotube grid has the function of structural health monitoring later. We use the piezo-resistive properties of the carbon nanotubes. So this process is repeated in order to place carbon nanotubes in the place that are considered better for this function. And when the layup is finished with AFP, we go into the reinforcement manufacturing. So after placing the reinforcements, a grid and a layer of the magnetic nanoparticles filaments are deposited that we will allow the disassembly by subjecting them to inductive fields. The magnetic nanoparticles will heat up and melt the matrix, the polymer matrix, in order to allow the disassembly of the reinforcement that will be placed also by FFF on top of these magnetic nanoparticle filaments to have a finished multifunctional component. So this is an overview of the process that we are going to develop here, but the objective of this will be to manufacture demonstrators of aerospace parts that will be developing in Dominion project. So we have two demonstrators from the end users, Atituri and BAE, that will be one spoiler outer skin panel reinforced with an omega grid printed by FFF, a novel reinforcement structure, and also landing gear door developed by BAE that will compose also of a skin panel reinforced with a lattice reinforcement structure, in this case also a novel FFF solution for the reinforcement structure. So for the moment, they are the first iterations of the prototypes, but well, they undergo more optimization and other considerations about manufacturability that will be important in this project also, such as manufacturability studies, such as head accessibility of the robots, as you can see here. It's important the accessibility of the printing head, in this case, the printing head to the structures. The curvatures will be important for the AFP manufacturer, as you can see here, in this case in a flat laminate, but this has to be assessed. Also the position head orientation in order to have a good trajectories, the compaction roller of the AFP that will have a lot of importance in order to transmit good pressure to the part. And well, minimization of other defects that can be arise for the previous aspects, such as gaps, overlaps, and well, surface, any surface defect that we can have here. So we will go a little more into detail here in the ATL AFP technology. It's really the ATL is the automatic tape layer, AFP automatic fiber placement are similar but not technologies, not the same technologies. And what we have and are going to use is more similar to a AFP, automatic fiber placement, that well we will use to develop monolithic structures that have a great structural performance to build the panels of the demonstrators. So in this case, you can see here our AFP system in AIMEN, consisting of robotic arm and AFP head. And that in this project will be improving with the developments that we're going to do here. So to start, we are developing an innovative laser heating system in order to obtain the desired temperature in the composite. It is up to it's more than 300 degrees. So we are working in between 300 and 400 degrees, and we have to heat up the composite tapes. So we are developing a laser scanning system that you can see here in red part that will control a laser beam that you can see in blue that will scan across the width of the tape. So in each point we have a control temperature regulating the power that it applies to each point. So we have an uniform temperature across the width of the tape. So you can see here in this part will be a picture of thermal imaging of the temperature that we take here in the nib point. Is the point we are pointing the laser. That will be the point where the incoming tape that comes out of the machine and the substrate meets. So we hit this point with this compaction roller. We apply the pressure and we move the head. So we have a deposit and consolidated tape on top of the laminate. So also for this project, we are developing a non-contact ultrasound NDT based on lamp waves that will be placed also in the AFP head. So we have an inline detection of defects. And we are also doing a thermographic imaging, infrared, for monitoring the temperature that you can see here, an animation of the compaction roller passing and applying heat here and the cooling down of the laminate that we will monitor and obtain data of this in just to obtain the correlation between this cooling process, the the crystallinity that we have for each cooling rate. You can see here a picture more or less the DSC crystallinity curves for different cooling rates, and we will correlate this with the mechanical properties. This will be in order to assure that we can obtain a good consolidation between the tapes that we place and the substrate in order to achieve the in situ consolidation that will be to have a finished structure in the time that we finish the layup. So every ply that we apply is a finished part. So we don't have to undergo an autoclave cycle after this. So in order to achieve this, we will be controlling the temperature by the laser heating and the heated layup mode. So this will be an overview of the AFP technology. So we can go now to the FFF technology. In this case, FFF is fused filament fabrication, where we deposit this filament that we feed through a printing head, and it gets heated in the nozzle that you can see here, and finally deposit on the substrate. For doing this, we are developing, well, IPC is developing an innovative nozzle concept that controls the temperature and the pressure inside the nozzle, so we can achieve good properties. And we are also installing a laser source heating system to heat up the substrate. This is in order to work in an optimal area of temperature and to have the substrate in a molten state to melt the substrates in order to have a good consolidation between the substrates and the molten filament that is being deposited. So we have a good consolidation and addition between those the fabrication. So we are also doing infrared thermography with thermocameras to obtain the information about the thermal distribution and cooling rates of the filaments that, well, you can see here an image. And yes, you also can see an image of the manufacturing with continuous carbon fiber of reinforcements in a part. Here you can see pictures of the AIMEN FFF head and the FFF cell that will be also a robotized one with a robotic arm. And here in the bottom right, you can see a picture that represents the idea of building reinforcement with FFF on top of the ATL laminate. So here we have a LM pike laminate, and on top of that we have a single reinforcement. In the final part we will have nanoparticles filament between those two, but we will have this concept with obviously more filaments reinforcing the structure. And this will be the overview of the FFF manufacturing. And now we can see an overall idea of the Dominio concept that, well, we talked about this before. Pablo presented it. The overall concept of the Dominio digital thread and data pipeline will consist on a data pipeline that will support the design, the manufacturing, and the simulation operation with ACHM. So in manufacturing, the idea will be to extract information from to control the process parameters with the laser system and the innovative nozzle that we see before, and obtain data from the thermocameras, from the ultrasonic NDT, and also from the roughness measurement that will be very important in the simulation, as we see in Ensam's presentation before. And all this information will be extracted and included in this knowledge-based system that will be developed in Dominio to extract the interdependencies between the design, the production planning, manufacturing, and the operation, and to assess a good quality of the manufacturing. This will be all from my side. So I think we have a few minutes for questions or.
Okay, thank you, Francisco, for the nice presentation. Actually, since we have some minutes, anyway, the next session is indeed the roundtable and open discussion, but there is a question in the chat box about your presentation.
Okay.
I will mention it now. Yes, so excuse me.
Yes.
Okay, so how are the carbon nanotube dispersed in the pack?
How the carbon nanotube disperse? Okay, I will.
Yes.
I will share again, and I will show.
From Sebastian.
That I think is better. Okay. So I hope you can see my screen again, right?
Mm-hmm.
Okay. You see my presentation mode or the full screen?
Yes, it's in full screen.
Okay, so okay, you can see here the picture, right? In this case, the carbon nanotubes are manufactured by Tortec in a continuous, well, in a filament. It's like a thread that is formed by the carbon nanotubes entangled, forming a thread. So we process this thread of carbon nanotubes, and we embedded in a well, we manufacture a full filament with the PEG matrix surrounding the carbon nanotubes thread that we can see here.
Sorry, so I'm unmuted.
Yes.
So it's not a single nanotube encapsulated by polymer.
No. It's a thread formed by several carbon nanotubes.
Ah, okay.
Yes.
What's the mass fraction then of carbon nanotubes?
Yeah, for being sincere, I don't know. So,
Okay.
well, maybe we can. I think that maybe in the open table it will be a good question. Maybe we can get the answer there in the open discussion later.
Can I ask another small question?
Yes, for sure.
Yeah.
So you're developing the laser scanning system. Are you
Yes.
feeding back the signal to the robot or to the laser?
Yes, the
For
signal
control
is
loop?
yes, it's a control loop in the laser. Yes.
Is this something that you do yourself, and do you have access to the controller of the conbility head?
Yeah, this is it's not controlled by the conbility head. Is an AIMEN development that is controlling a closed loop in the laser. So yes, the laser has backfeed. It scans as it goes scanning and applying the power. It also obtains the information about the temperature in the profile of the tape. So it's a closed loop control.
But so you can access the controller of the laser.
Yes, that's it.
But you don't need
Control,
the help of conbility. It's kind of open access.
yes, that's it. We control the laser by itself, and we could with conbility we only call for the activation of the laser. It's not the console.
Okay.
Just in the robotic program.
Yeah.
Yes. In this case, of course, in other applications, we can use a control by conbility, the conbility control also.
And in general, are you happy with the head?
Yeah. We're happy. We're working with the conbility head, and for the moment, it's good result.
Okay, good.
Yeah.
Thanks.
Fran, I guess that this question, I mean, I guess that there are several ways, there are approaches for controlling the laser. That's also for me to really understand. So our option is to not really interact with the robot, but just to make the laser deposit the energy needed. But at the same time, we have to know, or we want to record the position of the robot with the thermal input history, right? So somehow we are making interpretable the laser hitting with the position of the robot, right?
Yeah, that's it for sure. Yeah.
Mm.
Yeah, but I mean the control loop that we have in the laser is not controlled by the convertibility head, because the convertibility head also has control loops for controlling the temperature of the power of the laser with pyrometers. But in this case, we're not using that control. They have PID fuzzy controllers, but we are not using that. We are implementing the control loop is an AIMEN development for the Domino project. Yeah, but of course it has to be related with the robot in that way.